Okay. So, good afternoon. Thank you for joining this session. My name is Alberto, and today we are going to talk about this unsupervised free cat. A cat is not only the animal, but in this case is the software, how we call that in the language translation industry, the software to translate. I'm 36 years old. I started working more than 10 years ago. I've been at the university. I'm a master in computer science, and I'm working most of my career in startups. During the day, I look after as a SRE in the DevOps business unit of the company who sent me here, SourceSense, and also I'm a machine learning manager for the unit. My forte is in Kubernetes, monitoring, continuous integration, cloud, Hadoop, so big data, Python, everything which is around Jupyter Notebooks, scikit-learn, TensorFlow. At night, I attend in the spare time that I have 2 metal concerts. And there's something here. This diapositive one is just really annoying. Okay, it won't go away. Okay, very good. Great. So I would like to thank also the company who's sending me here. It's SourceSense. We are basically a consulting company completely devoted to open source software. We've been existing since 20 years, and we have various branches in Italy, and also one in London, so no more in Europe. And we are DevOps people, we are coders, we are data scientists, and so we take after 360 degrees of everything we can. So today the outline is as it follows. So we're starting with the need for a standard tool chain for translating and localizing, as we say, software project. Then I will talk about the CAT tool I'm bringing here today, which is MateCAT. And what's the problem with today's machine translation, which is the most fundamental supporting system for a translation pipeline? And what is the solution which is coming to the rescue? And what we have here practically. So why do we need a standard tool chain? Although there are a lot of solutions out there to translate documents and software, most importantly, it feels that too many times we have too many ways to skin the very same cat. And this is because a lot of people are not into the translation industry, so who doesn't understand reinvents from scratch. And this is always very dangerous because it fragments the efforts. And so the software industry, and particularly the FOSS industry, needs to adapt more to the industrial way of doing things, which is the only one viable one. And this is because the industry actors, which are the language service providers, the LSPs, have long set onto a consolidated set of processes, of technologies, and file formats. There's also even a consortium which is called OASIS, which standardizes the file formats and the interchange technologies that allows to build a viable industry for translation. This presentation is about exposing battle-tested technologies to the community so we can return back soon to what we love, which is hacking, and not coming up with new ways of translating a software or translating a document. So the standard tool chain for a translation company or an open source project that wants to be translated starts with a CAT, a computer-aided translation tool, which is an editor that parses a bilingual file. A bilingual file is a kind of an envelope container which represents a file which is in the process of being translated. So you put this file in this envelope, everything is extracted, and you can manipulate the strings, which is the text, the buttons text, the labels, the menu voices, but even a simple docx document. You can manipulate these strings into other languages. And among other things, it has to provide the 2 main capabilities, which is the tag editing capability. So you can manipulate the untranslatable entities like markup. if you think about it, a lot of the content in a well-formatted file is the formatting, which has nothing, doesn't need to be translated. You must not translate it. You must preserve it. Otherwise, you're going to break the markup. And so you have to manipulate that thing, leaving that untouched. And also, number two, format preservation. So you must convert from the original file to a bilingual system. Then you have to translate all the strings, and then you can pack the strings back in the original file format, preserving the formatting. You don't want to break the file just because you change the strings. Another really fundamental component is the presence of a translation memory. You can think of translation memory as a database of past translations that you can recycle or adapt for the incoming document which is coming here. And the idea is that once you translate something, you don't throw away all the singular translations, but you keep them because the next time you're going to make a second revision, for example, of dishwashing machine manual, you just want to reuse the very same sentences and just translate the new ones. It's a matter of style guide. It's a matter of preserving the experience. Like control panel from Windows in Italy is pannello di controllo. You cannot change that sentence to something else. Otherwise, all the Windows users who are accustomed to the kind of sentence appearing somewhere in the menu will be confused if you change to somebody else, like pannello, I don't know, pale controllo, I don't know, for the control. So you must preserve the style, you must preserve everything that is part of the experience of the software. And translation memory serves this purpose. And last but not least component, you need a machine translation, which is a server that provides translations on the fly, which is Google Translate, for example. So some dominant standards which are worth knowing is the XLAFE, which is the Exchange Localization file format, which is an XML-based file envelope that separates the strings from the markup. So you put a docx into an XLAFE envelope, then you have like the blob, the binary of the original file, who has been processed by removing all the strings and substituting that with placeholders. Then the placeholders are into a map that maps towards the strings. You have them for the original language you are coming from, but then you can add new keys for the other languages you want to go into. And so whenever you want to translate the document, for example, in English, you just add the keys for the English to that map, then you pack telling the software to read only the keys in that language code, and it packs back the translated strings into the original document. So replace the placeholders with the new strings. All the document is saved, and what you end up with is a file format with different language, which feels like kind of magic the first time you see it. I'm going to show it here. Then the TMX, which is an XML exchange format for translation memories. You want to export your translation memory and give it to another translator or to another member of the community. You use a TMX, which is a standard file format. And the last format worth talking about is the PO, which is the specialized file format for the getText library, which is a GNU tool, and is the one that you put the strings into, and the software is expected to find the strings in that format, so anything that compiles with the getText library is able to be localized in this way. When you start localizing a project, you look for the getText PO files. How not to do it? For example, iOS and Android are long-standing offenders because they came up with their own proprietary file formats, which is the localizable strings and the strings XML. And there are tools to convert this stuff to the PO format. So the standard workflow is that you come with an original file, you put it into a CAT tool or a CAT server, and that generates an XLIF container, which is the envelope of the original file. Then you query the translation memory or machine translation, and you fill all the content in it. At any time, you can export the container to an XLIF file and send it to an independent translator to have it translated. This is particularly important because you don't want to send the original file. You don't want the translator to gain access to the original file, which may be reserved, which isn't translated to. Also, the file may be so big, they want to split the load among 10 translators. So you have a 10 small XLF file with 10 parallel pieces of stuff. Anytime you can export translation memory in a TMX or the machine translation in a model file you want to deploy somewhere else. And at any point, you can take the XLF container with the strings that have been translated until that point, repackage back them into a translated file, which is the thing you want to go back to your customer or to the community if you're working in a project. So today we are showing our CAT tool of choice is MateCAT. MateCAT is an enterprise-grade, completely free and open source, web-based CAT tool. And it has been funded by the European Community in the 7th Framework Program. It costed 3 million euros and 2.5 years to develop. It started with a 4-people team, including me, for the very first release. It's currently open software, so you can find it on GitHub. And it's evolved and operated as a service by Translated, which is the company that took the tender to develop this technology. And so now I'm showing you this. So today I'm bringing you here, there is the hosted version, but the hosted version is not really interesting. So today we are deploying that on our laptop in real time. And this is the first thing I'm bringing here, which is Docker MateCAT. And it is actually a proper packaging of this tool as a Docker container. So it's easy to deploy that. So it's really easy. You just have to clone and issue these really small commands. So in this case now we are, whoops. Let's start bringing up the MySQL container. Let's then bring up, let's initialize the MySQL container. Testing if the container is connected. And there we go. Okay, everything is up. So my keyboard just switched to English, thanks to them effect. And then we're bringing up the rest of the tool. I've started with some settings, but you are free to customize everything. I try to move everything from the build time at runtime, so you can just change your runtime variable, and the tool changes accordingly. The only thing which is really nasty can be improved here, actually, is that it expects you to. It runs only on Chrome, but that is by design, okay. But it expects you to have a dev.matecat.com for a matter of cookies and where to find the API domains. That is hardwired in a configuration file. And I will make sure you can change your runtime in a later version. But for now, you just add the dev.matecat.com into your localhost, because your PC must know where it is. And this is the CAT tool interface. So here you can upload anything. And I'm starting with this Docker and Kubernetes presentation, which is a file in English about Docker and Kubernetes. And let's just load. Know that it's a, oops, sorry, this is my fault because I forgot one thing, to change the permissions. Otherwise, they are complaining. So the file has been uploaded. Now it's being converted to this intermediate representation. This supports over 72 file formats, so all the Office stuff, strings, CAD, as a really, really big array of formats. It does the conversion for you and packs back. So it's really nice. Now we start analyzing. And of course, you can sign in with the Google account. I put my development keys in here, and now it's complaining that this app is not verified because it's a development environment. Don't worry. A nice feature that this tool has is that it can scavenge for you your docs from Google Drive and have them translated and re-uploaded back to your drive, which is really handy. Now it's analyzing all the words in order to show, find for duplicated content, so you don't have to translate something twice, and for matches into a translation memory, which I have. and we just open the workbench. So here you can see I've partially translated some stuff, so it's locked. I cannot touch it until I unlock the string. But never mind, because there are other strings here. So for example, I click here, and I get a suggestion from a machine translation server, which in this case is Google Translate. So we can just accept the translation or not. So the new containers, we don't translate containers in Italian. Then we translate, and it goes to the next one. See, here we have the tags. These tags are the formatting of this PowerPoint. So the problem is that this string is in the middle of a tag, which maybe is bolded or maybe is italic, and I have to make sure that it stays in. So for example, Spring, deploy your Spring application. Spring in this case has been translated as Primavera, but is absolutely wrong. And in this case, Spring application are in between two different tags, two nested tags. So what I'm doing here is I'm leaving there as it is. So it's trying to guess all by itself. Come on. Okay, accepted. And I can go over and over and over until all the strings have been translated. Need space to store your images. Okay, fine. Anytime I can download the preview of how is it going, and it's just downloading the file. Now if I open it, you can see it has been translated in Italian, while all the formatting has been preserved, which is pretty much impressive. And there we go. So a critical part, all is good, but for the most of my time here, I've been relying on a machine translation server to suggest me the correct sentences. This because I just had to accept or edit the suggestions. This gives me a big productivity boost. But no matter how much data we translate, we'll never have enough memories to reuse for the new project which is coming. So machine translation system is here to actually fill the gaps, which are always more than you have. Machine translation are machine learning systems that are trained over data sets which are named parallel corpus or corpora. Parallel corpora serve as a bidirectional labeled data set. A parallel corpora is a very, very, very long list of sentences in one language, for example, English, and then a corresponding list of those sentences in the foreign language I'm trying to translate, for example, Italian. So I have 1 million sentences in English and 1 million the same sentences translated in Italian. And it serves as a bidirectional labeled data set because I show an English sentence and then I show the corresponding Italian sentence. But I can do in the opposite direction. I want to start from Italian to English. I start with the Italian string and I show as a label what you should come up with, the English string. The problem with this thing is that you have to feed this machine learning server. You have to come up with a lot of data. And this has been particularly made worse by the advent of the neural technologies. The neural machine translation, since it's a neural network, it requires a lot of data, which are in the hundreds of millions of aligned sentences, okay? A lot of stuff. So since the technology is pretty much the same for all the players, the winner is the one who has more data, which namely is Google, always. That is the only really serious provider of machine translation technology. All the others are niche players who pretend to be very good, but Google Translate actually is the top-notch player. They started first, they crawled a lot of data, they aligned a lot of data automatically or with manual efforts to bootstrap. Then they really came up with billions of words. So the problem is that we have to find this data, there are efforts to procure parallel data for free, which is the Opus, which is an open source parallel corpus. And it's a collection, an open collection of parallel corpora, which grow every day. For example, they crawl pages in different languages and align them. Or, for example, they take books and they align the sentences, even though they're not exact the same translation, because literature translation is not really the same. For example, you know a book which is really, really, really easy to align? The Bible. The Bible is has notation for all the versets and all the different chapters, is the most alignable book in the world. And it has all the languages in the world. So although its way of writing is a little old, it works very, very well. But the problem is that we have enough data to come up with a decent translation system, because we can just use this stuff. There are millions and tens of millions of sentences in this open corpora. But just for FIGS, which is French, Italian, German, and Spanish, if you have another language, for example, Norwegian or Sudanese, you have no way of coming up with a decent machine translation system. You just have not enough resources, not enough parallel resources. So we are stuck at a dead point, because the technology we have is very good to come up with translations, but only for a selected amount of languages. And since those languages are those who can benefit from the presence of a translation industry, there are more and more resources are created in those languages, because more and more documents and interactions are produced, and so the more and more data they have, it's a virtuous circle. And the same doesn't happen actually for Norwegian, Italian Norwegian, for example, or Japanese Hebraic, because there's no interaction with the Japanese culture and Hebraic culture, so you don't have an aligned data set. So you say, okay, what if we have Japanese English, and then English Hebrew? We can do like a pivot. We translate from Japanese to English, and then from English to Hebrew. Yes, you lose a lot of fidelity. Because it's like we have in Italy, we have a game, I don't know how you call that abroad, is the cordless phone, in which you say a sentence into an air to somebody else, and then the other has to tell to another in a ring of people, and then at the end you have to you have fun knowing what is the sentence that has arrived. Doing pivoting in machine translation is really the same thing. So you're just taking the output of a machine system and feeding it into the another machine, which will add a lot of distortion, and so you will not be very happy, because your translation will suck. So let's just maybe since we are in a dead end, we may take a step back. The dead end comes from the fact that we have a supervised system that needs labeled data. What if we just go with unsupervised training? Unsupervised training is a particular kind of a class of machine learning system which is not concerned with finding correlations between data and a label, but finding a hidden structure into a corpus which has no label. So in this case, we don't need the parallel examples to learn a language. It's not the way humans actually learn a language. So we learn Italian when we are our mother tongue language, and then we learn another language, but separated from Italian. It's not that they just relentlessly show us examples of all the lore that we can come up with in our mother tongue language, and they just throw at us English translations. For me, I'm Italian, until I learned English. I just learned the English separately, and then I started doing my mapping between the two languages. And then we can do actually the same. How about learning two languages and then try to map between concepts, which is easier, because it's easy for me just to get a very, very vast corpus of just Italian, just Norwegian, learn those independently, learn a model of how those languages are structured, and then try to put some links, some bridges in between when I master the two languages. The problem is that we are dealing with a machine. So in order to map between languages, a computer needs to build a representation of that language. And how can that be accomplished actually? We may use language models. Language models are technology that allows a machine to come up with a structure, a hidden structure, because we're just showing it data samples and not teaching him the rules, and builds a model of how a word relates to another. And word embedding is a technique that maps every word into a vector space. Remember geometry at school where you have all these shapes in 3D environments which are vectors. So these are an array of numbers, and when the numbers are close, two vectors are close in space. Words with near meanings will have near vectors in that space. So, for example, I don't know, Paris and Rome will be near in the space of the capitals, because Paris will be and Rome will be very far from Milan, for example, because Milan is not a capital city or anything. So Paris, Rome, Berlin will be very near. And Milan maybe will be near Frankfurt among the dimension of all the cities who are not capital to anything. Boy and man will be near because they will be on the dimension of the type of sex. It will be a dimension of just two numbers, actually, like a binary dimension. But anyway, we have these very big vectors of 300 dimensions, and we come up with a way to map from a word to this stuff. And we can do even crazy things. Since these vectors and numbers, they actually allow us to do computations like you take the vector of Paris, you subtract the vector of France, and there are numbers. You then add the vector of Italy, and what you get is a vector which is almost the same as the vector of Rome. And this means that if we analyze enough sentences in one language, we start to develop a very structured model of how that language works internally, which is a language model, our language model that we need. So we could induce a parallel corpus between two independent languages by just mapping concepts between spaces, in latent spaces. And we can bootstrap with a vocabulary. For example, we have a vocabulary for Italian and Norwegian, and so we know which some words translate into another. And you can just bootstrap from them, and then you can start mapping similar concepts. Or you can just use unique entities and frequencies. So the article has the very same frequency as the Italian corresponding article, which is il. So you can home has the very same frequency I can expect in a corpus as casa in Italian. So we can just use these as heuristics to guide our mapping in this very big latent space. So a very legit question is, won't the result be really, really, really noisy? Because you will end up with a lot of false positives? Yes, but we could use statistics to compute means and among how many times house seems to align with dog or to casa, and infer the true positive, throwing away all the false positives. And here comes the phrase-based machine translation, which is the old technology that was completely scrapped away when we came up with neural machine translation. The phrase-based machine translation had revolved around the concept that co-occurrences of words are statistically significant. For example, you see this character here. What do you think is the translation of that character? Shrimp, because it's the only character that occurs always. So you can assume that this is the translation of shrimp, and this is somewhat broccoli. If you happen to meet broccoli again in a word, in another sentence, and you just see this one, maybe this is broccoli and this is a particle, like some connective that it's used, it's peculiar to the Chinese language. And this is the way we used to train the old Google Translate. Now Google Translate is narrow, but in the old times it was based on this technology, which is a toolkit, an open source toolkit, of course, which is called Moses, and has been developed by University of Trento, University of Edinburgh. So the co-occurrences counts between words and sequence of words, because I've been at school. School can align with scuola in Italian, but also I have been. It's a sentence that is always translates in sono stato in Italian. So I can always count not only the co-occurrences of words, school, scuola, but also I've been, sono stato. And so I count the phrases. And the phrases, I treat them as a unit of translation. And that is subject to co-occurrences counting too. So I can use those to calculate the translation probabilities. A probability is just the idea that 7 times out of 10, casa is observed to co-occur with house. And that's a probability. So I can just come up with the probabilities and choose the most probable sentence among all those who get to be aligned. These probabilities are always annotated in a database, a special database, which is called phrase table. Creating a phrase table is the most expensive operation of phrase-based machine translation. So the Moses toolchain is based on 3 technologies, which is the language model, ERSTLM or CANLM, is the language model that calculates the probabilities of a sentence being meaningful. Then we have the aligner, which is Giza, and later was superseded by FastAlign, and Moses, which decodes the incoming message. Moses projects the input sentence over a phrase table to retrieve translation options. Searches among all the different options, guided by the language model as a heuristic, and then stops by itself when all input sentence has been covered. And today we are presenting the second technology, which is Monoses. Monoses stems from the paper from these 3 scientists, and it's basically a toolkit to create a phrase tables from 2 monolingual datasets through word embedding. Then it creates a Moses model with this noisy thing, does some fine-tuning, and then iteratively augments the dataset by translating itself. And so you can start with 1 million sentences, and you rapidly go to 10 million sentences because you try different combinations between sentences that you have started with. It's noisy, sure, but the sheer amount of data that you come up with ends up averaging out the noise in the long run. And this is what I brought today. So the second demo that I'm showing you today is Moses. My small contribution has been packaging this really wild research prototype into a Docker format, so it's easy to deploy, it's easy to use. You have the pipeline to train, so you just take 2 big text files with all Italian sentences and all Norwegian sentences, for example. And these sentences must not be related to each other. You just take Italian Wikipedia and Norwegian Wikipedia, or all the news set of, for the Norwegian, for example, and you stash in 2 separate files. They don't have to be parallel. They have to be monolingual. Then you launch the training. Passes a week. And when the process is finished, you will have several gigabytes of files inside this training directory, which is the models, the phrase tables. And then you can launch this translation server with the following syntax. You have to point it into the directory of the model. And you can now query your server with the following. So you have this API, which is another thing that I've built, because Moses has no API server, per se. So I built a Flask-based Python HTTP API. Please note that you have the verb here, the query, which is Ulver in this case, and the source language. Did I say Norwegian? This is Swedish? Yes, this is because Moses doesn't have a Norwegian tokenizer to analyze the sentence, but Swedish is really close, so I used the Swedish tokenizer. Sorry about that. And the target in Italian. And since this server is actually online, I can also provide a working demo here. It's really slow, because in this first version, it tries to load the model in memory. Each time it's run, then the memory is thrown away. You take another sentence, is loaded in memory another time. Ulvert is the translation of wolves, I lupi. And these are JSON output you have here. So, yeah. Now, in order to show you how this thing works, I have to go here. And then select Swedish. Then I go here. I try to disable the lookups because I'm purposefully using a wrong language. I have to fix this someday, so I don't get suggestions for the Swedish. And then I add the empty engine. I choose as the provider Moses because I try to imitate the Moses HTTP proprietary API. I try to just implement it. I add here, engine name, which is Moses. Okay. And this is the server. A key, you just type a dummy, you don't need it. Okay, now we have to look for a file which I have somewhere and I actually forgot where I stored it, which is embarrassing. And I think I lost that file. So, okay, I know I have a Norwegian file right now to show you, but the idea is that you will end up with a very, very, very slow server that will actually provide translations to you, not the Google Translate speed, very, very slower fashion, and the translations are not even perfect, but are good for a starting point to start translating your software. And the advantage of this is that you don't, even if you are Norwegian or Sudanese, so you have a very, very small presence online in terms of amount of data produced and parallel data produced. With this kind of technology, you can just throw in enough data from books, from articles, from cooking recipes, from subtitles of movies, and that you have a lot of. If you go in Opus, the parallel corpora, and you take only the monolingual part that you are interested into, then you might be able to actually build a very, very huge model. Proof is that I've launched the model that I show you today. Is just a test model with a few data. The serious model for Italian Norwegian has been running for 5 days and hasn't finished the training yet. So I cannot really show it to you because it's just training on a 50-core machine. Has been running for 4 days on 50-core machine. It's not looping. It's just that it does a really, really, really long refinement process. So it induces this phrase table, takes 10 hours. Builds the first model, 20 minutes. Then starts doing some fine-tuning, some parameter fine-tuning, and this takes approximately another hour or so. Then goes to the monolingual corpus, translates it with the model it has built, and generates 2 parallel corpora. Because it goes to Norwegian, applies the Italian-Norwegian model, and generates a corresponding Italian translation. And does the same for the other. And then now you have 2 very big parallel corpora that are used to augment the rough model that you started with. It's like a Viterbi training. You bootstrap with a rough model and use yourself to improve your own training. So if you supplied, like me, 700 millions of words to this model, it takes a long time to translate 700 millions of stuff. Then you do another fine-tuning, and then you do that again. Iterative 10 tuning iterations for 3 iterations of back translating all your corpus from scratch. Takes a ridiculous amount of time, so I hope to actually post some updates on how the experiments went, actually. So, in conclusion, today, what we had here, so we have a Docker packaged version of Moses, which is ready to use to generate a training set. We have an HTTP API server to query the model obtained this way, and it's all available in this repository. And then we have a packaged version of MateCAT tool, which includes also a MySQL server, an ActiveMQ instance, various daemons to perform the analysis and the translation in the background, and an Apache 2 web app with a PHP, a very humongous PHP web app. Runs in Docker Compose, but I aim to support Kubernetes, so you can just deploy that anywhere, and you can start your own very, very small LSP at home for your open projects. Kudos to the 4 knights, which are those who were portrayed in the cover of my presentation, which is Philip Cohen for inventing the phrase-based machine translation, Thomas Mikolov for inventing Word2Vec, which is the mapping and the language model with those vectors, Adam Paschke for inventing PyTorch, without which we will never be able to actually train anything narrow, and Michael Artetxe for putting all together and be the author of the paper I took inspiration from. Thank you very much. So, are there any questions? Here's the faces of the people. The cover is Sgt. Pepper Lonely Hearts Club Band. Yes?
What about the construction of the phrases? Because we have seen today that, for example, in Italian, there was a word before another word.
Yes.
And
yes.
in English is not.
Yes. So your colleague is asking, when you translate a sentence which has some markup into another language, who happen to remix the words in a different order, the tag formatting is not preserved because, for example, you may end up with a sentence between tags which is split into different sentences with something foreign in between. Then you should duplicate the tags. So this is a problem that has been solved by Christian Bach, which is a Google Brain scientist and worked in the University of Edinburgh. And he basically employed a trick. So he factorized all the tagging. If you have a sentence, 5 words are tagged, you put tags in each separate 5 words. So you multiply the tags so that each single word is bolded independently. Then you translate, you let those be remixed, and then if you happen to have in the target language a sentence with 2 tags, you can collapse them in 2 words between 1 tag. You solve that in that way. This technology that I have developed doesn't feature that trick, which is one of the first things I'm going to add, actually, because it's a very naive trick, but it works very well, actually. And so I will scavenge that from the MateCAT project, because the MateCAT project, this MateCAT, means Machine Translation Enhanced CAT tool. And it shipped the original project when it was a research project with an array of little stuff like this who actually improved a lot the quality of the engine. I will try to go back in the old repo when it was a research project and pull those back in. Now I've developed from scratch because it was just much easier for the purpose of this conference.
So you mentioned that you don't need parallel corpus to train monosis, but I imagine if you would use the parallel corpus, the training stage would be a lot faster because it can just test whether it's correct.
Okay, so your colleague asked, you don't need the parallel corpus to train monosis, but what if you happen to use 2 monolingual corpora, which is in fact 2 parallel corpora? Will it be easier or faster? Not faster, but it will be less noisy. Less noisy, because you will end up with good quality mappings, which usually they end up for being very noisy when you use monolingual corpora, because you end up with a lot of false positives. If you happen to use a parallel corpus, those mappings end up for being high quality mappings. So your training is actually of a better quality. You end up with a better model with less noise. And so you have to spend less time doing fine-tuning and back translation, and you don't have to create this really, really, really huge amount of data only for the sake of a Monte Carlo sampling that averages out the noise, leaving the good stuff in this place. Sure.
I have a question regarding the MateCAT tool. You already support a couple of formats. So what would be the process to add another format, for example, a XML-based format, to be also the base for translation?
I think I didn't understand the question.
You support, for example, PowerPoint.
Yeah?
For example, it's a file format, as I understood, it's translated to XML, or
So all of these files, which is the Office, the document, the Excel, PowerPoint, but also web pages, but also scanned files, it's true only if you put an advanced filter, which is proprietary of translated, and it does OCR or PDF. You can also just translate directly a TMX or an XLIF, and also desktop publishing stuff, and various localization formats like the properties and the where is the strings. So all this thing, whenever you put something in, an XLIF is generated behind the scenes, which is the envelope container. All the strings get pulled out, and they are inserted in a temporary location. When you translate, you replace those strings, and then when you do download or preview, those strings get packed back into the XLIF. The blob, the file, is just a matter of replacing placeholders and packing all the binary in, and you end up with a PowerPoint or a docx file in the end.
yeah, but what would be the process to add another file?
Add another file format. Okay, so the real question of your colleague was what is the process of adding another file format? You basically have to implement a new class behind, which is the class for that file format. The idea is that the interface expects here's a blob, give me the XLIF strings. So you just have to implement that kind of process. It might be really easy, for example, if it's, I don't know, YAML or JSON, because you just have to, you can come up with a template XLIF, and you convert a JSON into an XML in the format XLIF. So you can just take the strings and you paste those in this kind of format. If it's a more advanced format, and I'm coming up with the most difficult format out there, which is the AutoCAD. AutoCAD is a total nightmare because it's undocumented, it's heavily binary, and the strings are basically shredded everywhere in the thing. Then you have to come up with something that is able to read the strings, place a placeholder in the original file, and you pack this into an XLIF. And then you construct the sentences out there. I can show you an XLIF because it's not really difficult once you see it. Here we are. Come on, Wikipedia. So as you see here, an XLIF file, you should have a very big blob, which is the binary basis 64 encoded version of the file, with the placeholders already put in between. Then you have units, which is a translation unit, a sentence, which has always a segment with a source and a target. So for example, unit 2, segment, an application to manipulate temporary XLIF document. And here you have the corresponding target. This file is all from English to Japanese because of this header here. And then you go down and you keep having units, segment, source, and target. Units, segment, source, and target. This is the very basic unit of work. So if to come up with another way of producing an XLIF from a proprietary file format, you have to come up with a way to construct this XML. Once you have the sentences, it's really easy. You can compose this XML, and it's easy. The very difficult thing is that starting from this stuff, you just have to find a way to take out strings, put a placeholder in it with the ID of the unit you have here, and then you have to base64 encode and stash it here. Let me just show you a real one, because since we are in, I can show you this a real example of something we have here. No, this is a PowerPoint. Loading, loading, more loading. Okay. So here you can see the translation units. Which this is the XLEF version 1.0. The one I show you on Wikipedia was the 2.0. Sorry for the mismatch. Guys, my GPU is crunching. How big was this file? In the meantime, I'm just okay. Set wrap. Okay, here you can see this is the base64 encoded file, the PowerPoint file encoded as a base64. If I take this one and do a decode, I can see the binary PPTX. Woo, man. You can see the editor here at the 100% CPU. Okay, and here you have all the different translation units. When you have the source, Docker and Kubernetes, and with the segment source and the target, Docker and Kubernetes has been basically generated as a copy of this one. So when you translate, you actually write here. You write into a database, and when you export, you pack all the original strings in the place of this one. You can see even the tags here, the G tags that were showing inside the editor box. This is a very nasty file format with a very heavily documented standard. You just use this as a working table or as a workbench, and then when you have all the strings, base60 decode this one, substitute all the placeholder which point to a single unit, save the blob as a file, and you have hopefully translated file format output. This is the most complicated process in extending this CAT tool, but it has been done for each of these formats. Any other questions? Sure. Okay.
I just wanted to know what's the lowest resource language you've tried, and does it work still well?
I chose Italian Norwegian because I knew there were not a lot of resources, just some millions of words. For example, Italian English, which is huge, is 80 millions of sentences. Then times 10 for each word, you go 810 millions of sentences. Italian Norwegian has 12 millions of sentences, 6 millions. And then because I was listening to Ulvert, actually. That works. It actually serves. The lowest one which doesn't work, it's Sardinian. I tried to translate in Sardinian, but with 10,000 sentences, it's impossible to come up with a mapping with 10,000 sentences. You need some millions of words, but it's easy because you just need to crawl Sardinian websites, Sardinian books, and stuff. It's not difficult to find the monolingual corpora. The real challenge is to find the parallel corpora, but this technology turns the problem into scavenging monolingual corpora only, which is the more content you can just crawl in just one single language, totally unrelated with the other language you want to crawl, it's just an easier task.
Yeah, so you say that there's enough Sardinian content on the web already to find millions of sentences.
Yeah, Google has it.
Yeah, but they have some content that you don't have access to.
Sure, like Google Books, for example. They have crawled and aligned 1 billion words in various languages with Google Books. And that is the top source of their translation quality. when you actually are on Google Maps and you bark a random address inside Google Maps and it understands you, that's because it has a 1 trillion word language model built. It's just so much data that it's always able to understand you because it's always seen something. So Italian region works. The model I wanted to show you is still training. Sorry about that. But the idea is that it takes always weeks of training, but in the end you will end up with a model trained on a lot of data. Moses, since the Moses is the last chain of the ring of the chain, is not the best translation software server out there. It has been superseded by the narrow machine translation, which is much more fluent. But since Moses is phrase-based, the counts are made as discrete counts. So it's always able to come up with the probabilities, even in absence of huge data examples. It's a discrete system opposed to a continuous in the mathematical sense system for the neural networks. The translation quality is lower, but it has a score of 26 in a BLEU scale, which is the scale for translation quality. Google, with the neural, achieves 40 points, which is outstanding, but 26 are okay for start translating, for start drafting. I think our time is up. Thank you so much for attending here.